Stewart was a Scottish mathematician, and in the year 1746 he discovered a remarkable theorem in geometry. I mean, truly amazing. And let's look at how it goes. Okay, we have some triangle like this. Let's label the points. Let's label it according to classical labeling schemes. So A, this side is little a, this side is B, little b, this side is little c. And let's draw a line. This is called a Cevian line. We'll talk about Cevians later some more. We can actually, it doesn't have to look like it's going through the middle. It can go through anywhere. And let's make this proportion m and this n. Now, intuition tells us that there's something deep going on here. When m becomes smaller, then this line here, p, gets longer, and the other way. See, as n becomes smaller, then this line p gets smaller until it becomes b. Whereas here it gets longer until it becomes as long as c. So there's some kind of constraint or some relationship between p, a, b, c, and proportion m and n. And it's quite complicated. And it's Mr. Stewart from Scotland who discovered it. And it looks like this: a p squared plus mn equals mb squared plus nc squared. We want to prove this. This is a very interesting proof, and we need some tools before we can do anything. We want to first use the cosine law, which is like this. I'm sure everyone knows this. Okay, this, we have some triangle here. R1 is here, R2, and this angle is theta, and this is R. And it's like a generalized Pythagorean rule relating the lengths of the sides in terms of the cos of the angle theta. Now, usually students just memorize this. I want to prove it, and I know you've seen proofs of it before, probably had to do it in a test or competition. So I'm going to show you a proof that you've never seen before. Okay. And the next thing that we're going to need is this, that cos pi minus some angle phi, or theta, maybe consistent labeling, is equal to minus cos theta. We have to prove this also. So we're going to prove these two tools, and after that a whole bunch of algebra, and we get Stewart's theorem. So let's go to the other board and start working on this. Okay. I have here a little triangle. We have some angle theta. This is R1, this is R2, this is R, and I want to prove that R squared is equal to R1 squared plus R2 squared minus 2R1 R2 cos theta. And we're going to use complex numbers. And if you don't know anything about complex numbers, well, this is your introduction. All right, let's draw the plane for complex numbers, and I'm going to have a complex number z1 here and complex number z2 here. And this complex number, I say that this complex number has the same length as z2 minus z1. Let's calculate z2 minus z1. So we reflect this down. Well, it's not really a reflection. We take the negative of this. This is minus z1. And now we use parallelogram rule. Let's see if I can do this properly. Parallelogram rule like this, and we end up with z. The sum here is z. Now look, it's the same as this. This length and this length is the same. So if this length is r, then this length is r. So the norm of z squared is r squared, the thing that we're looking for here. The norm of z1 is r1 squared. The norm squared of z2 is r2 squared. The norm of z, as we now just showed, norm of z squared is r squared. And remember, norm of complex number is z bar. This is norm squared of complex number. Length squared of complex number is z bar. Okay, let's get to work. Let's look at this diagram again. Remember, this here is z. It has the same length as the thing we're looking for. Okay, now this angle here, we'll call it phi 1. That's the angle of z1, the angle of complex number z1. And this here we'll call phi 2. That's the angle of complex number z2. And look at this. This is theta. What is theta? Theta is phi 1 minus phi 2. Let's keep that in mind. You subtract these two. This is phi 1. This is phi 2. I subtract them. I get theta. Okay, great. Let's continue now. So Z1 is R1e to the I phi 1. Z2 is R2e to the I phi 2. This is complex polar form. And Z2 minus Z1 is R2e I phi 2 minus R1e I phi 1. Great. Now, this is Z. We want to find z bar because that's going to be r squared, as we have argued. So this here is r2 e to the I phi 2 minus r1 e to the I phi 1 times, now complex conjugate of this thing, okay, r2 e to the minus I phi 2 minus r1 e to the minus I phi 1. Let's be careful in how we multiply these things. Let's do this and this first. So we end up with r squared is r2 squared e to the, now this plus this exponent is 0. Okay, now let's do these two. This plus this times this, negatives cancel out, I get r1 squared e to the what? I phi 1 minus I phi 1, that's 0. Great. Okay, now, next. This times this. I get minus R1, R2, e to the minus I phi 1 minus phi 2. You see? Let's look at this carefully. This times this. Okay, if I factor out, if I distribute this minus here, minus I got this one, and minus cancel out, I get that. Okay, it's true. All right, I have another term here, minus. Now, I did this one. I have to do this one, and this one. So that's minus R1, R2, e to the I phi 1 minus phi 2. There we go. Isn't that nice? All right. This simplifies now. This is just 1. E to the 0 is just 1. So I get R1 squared plus R2 squared minus R1, R2. Now, this here is e to the I. This is e to the I minus theta plus e to the I theta. You see? Because, look back here, what is theta? Phi 1 minus phi 2. So I use that here. Here it becomes minus I theta and I theta. Great. Now I use Euler's formulas. R1, R2. This is cos theta minus I sine theta plus cos theta plus I sine theta, like that. So this cancels with that, and I end up with r squared, r1 squared plus r2 squared minus 2r1 r2 cos theta. Ta-da! Well, have you ever seen a proof like that before, using complex numbers? Really nice. Now, let's do the other thing that we need to show. We need to show that cos of pi minus phi equals minus cos, let's call that theta, because we're going to call it theta in subsequent pictures. Okay, We'll do it two ways. First way is the graph of cos. That's 2 pi, that's pi. Now cos is an even function. So cos of x is equal to cos of minus x. That means cos of pi minus theta is equal to cos of theta minus pi. Now that's a right shift in the right direction. So I take my function, I shift it right by pi, and I get something like this. And you see, when cos theta is negative, cos pi minus theta is positive. So they're the opposite. When one is negative, the other one positive. Therefore, cos pi minus theta is minus cos theta, as we promised. There we go. Now, another way, again, let's do it another way. So it's good to do the same thing in many ways, because if you didn't understand it the first way, there's always the second way. So we have a triangle, angle theta. This is x and r. Cos theta is x over r, adjacent over hypotenuse. Now, if we go all the way out here and do pi minus theta, we end up with the same kind of triangle, except it's minus x and r. So cos pi minus theta is minus x over r, but this is minus cos theta. Ta-da! Okay, so in either case, we have this. So now we're ready to go back to Stewart's theorem, and we see that this here is theta, and this here is pi minus theta. So we can take advantage of this cosine stuff and get to work. Let's use cosine here. We have r1, r2, and r. Okay, so we have b squared is equal to p squared plus n squared minus 2pn cos theta, right? See, look, this is r1, this is r2, and this is r, and that's theta. It's the same form as what we have here. r1, r2, theta, and r, and then cosine law. So I get this one equation. Now I need another equation. Yeah, I use this angle here. Okay, this is like r1, r2, and c is r. So I get c squared is r1 p squared plus m squared, that's r2, minus 2pm cos pi minus theta. But we showed before cos pi minus theta is minus cos theta. So this actually is p squared plus m squared minus plus 2pm cos theta. Now what I can do is isolate cos theta from equation 1 and equation 2, and I can equate them, and I get some algebraic kind of expression which can be simplified into Stewart's theorem. Okay, so let's do that. From equation 1, I have b squared minus p squared plus minus n squared divided by minus 2pn equals cos theta. And from equation 2, I have c squared minus b squared minus m squared divided by 2pm equals cos theta. So I say 1 equals 2, equation 1 equals 2, and I get this thing. b squared minus p squared minus n squared divided by minus 2pn is equal to c squared minus b squared minus m squared over 2pm. Now I can cancel out this, and I'm left with b squared minus p squared minus n squared over minus n equals c squared minus p squared minus m squared over plus m. So let's continue. I'm going to put that minus sign, and let me cross multiply. Well, let me put that minus sign away first. So I end up with minus b squared plus p squared plus n squared over n equals c squared minus p squared minus m squared over m. Now let's cross multiply. I have m minus mb squared plus mp squared plus mn squared equals nc squared minus np squared minus nm squared. Okay, let's take the negatives on this side and the negative on the other side so we get all positive terms. All right, let me try to stand back and do this. mp squared plus mn squared plus np squared plus nm squared equals mb squared plus nc squared. Now, I factor this out. I get m plus n, you can verify this, p squared plus mn. You can verify by multiplication that this, equals mb squared plus nc squared. Now, the final step, this. What is m plus n? Go here, have a look. M plus n equals a. A, p squared plus mn equals mb squared plus nc squared. There it is. Ta-da! Stewart's theorem, 1746, Scotland. If you like this, if you like Stewart's theorem, if you like Scotland, click like and subscribe for more videos.